Academy. Today we'll be looking at conditional probability. Okay, the probability where we normally say A happens given that B, or what's the probability that B happens given that A had already happened. So those type of conditions, when we give a condition like given that, then we will it's like without replacement. When we say conditional probability, it's like when we talk about we give you more information about an event. So the probability of that event happening originally and the probability that you'll be given more information will now be different. The results will be different from what you had previously of an event happening, something occurring. So conditional probability is when you're given more information, more and more information about the probability. So the outcome will be different. So, but before we, it's also used for combined event. Remember, one thing you should bear in mind is that conditional probability is used for without replacement. Let's say, for example, there are 3 blue balls in a bag, and there are 8 red balls in a bag. Okay, a ball is chosen at random without a replacement. Okay, with replacement, it's not a conditional probability. When we say without a replacement, that means a conditional probability. So a second ball is chosen. For example, if you say a ball is chosen at random, what's the probability that the ball is blue? Meaning 3/11, because they are total. The first ball that is chosen is blue. What's the probability that the first ball that is chosen is blue? So that will be simply 3/11. Why? Because there are three blue balls, there are 3 blue balls in the bag, and there were 8 red balls in the bag, right? There were 8 red balls in the bag. So if we ask what's the probability that the first ball that is chosen is a blue one, randomly we chose, what's the probability that the ball that we chose is a blue ball? Okay, randomly means without looking. You just dip your hand and you shake it, just dip your hand and pick one of the ball without looking. So that's random. It's random. It's not like selective. So what's the probability that that is blue? That ball that you chose randomly is blue. So you know the number of blue. The first ball you chose is blue. So the first ball, your total number of blue is 3 over total number of balls in the bag is 11. So the first ball. Now what's the probability that the second ball is blue given that the first ball is also blue? Now here's the condition. What's the probability that the second ball chosen randomly is also blue given that the first ball that was chosen was also blue? Now here, probability of second ball. Okay, this one was first ball. Okay, even if we didn't write first ball chosen, because 2 balls were chosen from the bag, one after the other, without replacement. Okay, so now here, probability that the second ball chosen is blue, given that the first one was blue. Probability of the second ball chosen was blue, given that the first one chosen was blue. Now, if the first one chosen was blue, it means that it will now remain 2 blue in the bag. If the first ball that was chosen was blue, it will remain 2 balls now. So the probability will be 2 over total ball. Since you remove 1 ball, total ball will no longer be 11. Total ball will be 10. So probability that the second ball is blue, given that the first ball was also blue, is 2 over 10 now. Which 2 over 10 means 1 all over 5. 2 over 10, if you simplify, you get 1 all over 5. So this is a conditional probability. Why is it a conditional probability? We are asking what's the probability that the second ball that is chosen without replacement, you take the ball out, you don't put it back. The probability that the second ball chosen without replacement is blue, given that the first one was blue. If the first one was, okay, if the question goes like this, what's the probability that the second ball chosen, given that the first one was red? If the question says, what's the probability that the second ball chosen is blue, given that the first one was red, okay, the second one is blue, given that the second one is red, the first one was red, meaning the first time you chose the ball, if the first probability of the first one be red is 8 over 11, right? Probability of the first one be red, the first ball chosen be red, is 8 over 11, because there are 8 red balls and there are a total of 11 balls. This is the probability of first ball chosen at random be red. This is the probability B red. Now the question is, what's the probability that the second ball chosen is blue, given that the first one was red? Now, since the second ball you chosen is blue, the first one you chose was not blue, it will still remain 3 blue balls, because the first time you chose a ball, blue was not picked. Blue was not picked. So it was red that was picked. So it will still remain 3 blue, not 2. It will still remain 3 blue, because the first one you chose was a red one. Probability of the first one was a red one, which was 8/11. Now, there's probability of this one. Remember, the total ball is now remaining 10. It's remaining 10. Why? Because this is the second ball. You've chosen one ball out in the first instance. You've taken one ball out in the first instance. The second ball is the one that is blue now, which is total blue over remaining 10 balls that is remaining. So this is a conditional probability. So when we get probability of this is this, given that the first one was this, all this type of probability, they are called conditional probability. They are called conditional probability. So now let's listen to this tutorial to give us a huge clarity on conditional probability.
So in this tutorial we're going to look at combined probabilities, which is what you have to deal with when you have more than one thing happening. So 2 trials, if you like. Remember, a trial is an experiment, a probability experiment. And ways you might approach this are, well, you might use a tree diagram. Okay, you don't have to use a tree diagram, but it sometimes is a good idea, remembering that on each set of branches the total probability must be 1. You're going to need to make a decision if 2 things are happening and it involves picking things out of a bag or a hat or a chocolate box or something. You need to decide whether the items are replaced. So is the first thing replaced before the second thing gets taken out? And if they're not replaced, remember that the numbers, particularly on the bottom of the fractions, go down by 1. We'll have a look at one of those in a minute. Whether you use a tree diagram or not, it's always a good idea to write down the probability you want with and or between the things, okay, as you would naturally say it. And then, once you've done that, and is always times, and or is always plus. Just pausing to note that the and rule, and is times, works for independent events. In other words, the first thing doesn't affect the second thing. And the or rule works for mutually exclusive events, which means the 2 things can't happen at the same time, like a head and a tail on a coin. They are mutually exclusive events. And there is a trick you can use, a couple of tricks here. It's often quicker and easier to use. Well, if you want to find the probability that something doesn't happen, so the probability of not A, it's often easier to find the probability that it does happen and subtract it from 1. And similarly, if you want to find the probability that you get at least 1 of something, find the probability that you'd get none of that something and subtract that from 1. And often the question will highlight a word which tells you to use that trick. So anyway, let's apply this to some questions. So here we have the box of chocolates with 8 dark chocolates and 4 milk chocolates in it. So that's 12 in total. And 2 chocolates are taken at random. Now, it very clearly says they're both taken out at the same time, but we treat that as one after the other without replacement. So these are clearly not replaced. In my experience, in my household, chocolates are never replaced. And we're asked what the probability is that they are different types. Well, we don't need a tree diagram necessarily, but we are going to draw one just to show you how they work. So, first chocolate can be dark or milk, and we put the probabilities on the branches. So the probability of a dark chocolate is 8 out of 12, and because there are 8 dark chocolates and 12 chocolates in total. And then the probability of a milk chocolate is 4 out of 12, for the similar reasons. And just note that, of course, those 2 things do add up to 1. And then we need to put a second set of branches on, okay, after each choice here. So if it's dark first, it can either be dark or milk second. And if it's milk first, it can still also be dark or milk second. And now, because we're without replacement, we need to be careful with the probabilities. So how many dark chocolates are left if we've already taken a dark chocolate out? Well, the answer to that is 7. But how many chocolates are left? Well, that's 11. And that's what I mean by the numbers going down by 1. The number on the bottom always goes down by 1 when it's not replacing, when we're not using replacement. And depending on which one you're taking, the number on the top might go down by 1 as well. Now, what about milk chocolates? Well, there are still 4 milk chocolates left and 11 chocolates in total. And again, check that those two add up to 1. For the second set of branches, well, there are 8 dark chocolates left, but only 11 chocolates in total. And now there are only 3 milk chocolates left if I've taken one out, and 11 in total. And again, the numbers are going down by 1. Now, whether or not we've drawn that tree diagram, we should now write down the probability with ands and ors. It's perfectly okay to use D and M for dark and milk. So, what's the probability they are different? Well, it's D and M, or M and D. Now, if you think those two things are the same thing, just have a look at the tree diagram. There are clearly 2 routes through the tree diagram, and you can see there are 2 ways of getting different chocolates. So although you end up with one of each, you've got them in a different order. So let's now do the probabilities. So the probability of a dark chocolate, according to my tree diagram, is 8/12 and is times, and then following that first route through, I get 4/11 there. So that's that route there, and we're multiplying because it's and. It then says or, so we add, and then we follow this route through the tree diagram. As I say, you may be able to do that in your head without a tree diagram, but it's 4/12 for the milk chocolate, and then 8/11 for the dark chocolate. And if you do all of that, which you could do in your head if you like, that is 32 132ths plus 32 132ths, they turn out to be the same thing, which is 64 132ths, and that does in fact simplify to 16 out of 33. So there we go, there's an example of a combined probability question. Let's have a look at a slightly different one. Here we have a biased coin landing on heads 70% of the time. So the probability of a head is 0.7, and therefore the probability of a tail, of course, is 0.3, is it not? So let's actually just write that down. So probability of head equals 0.7, and the probability of a tail, which in fact you could call not head, head dashed, h dashed, is 0.3. Okay, now notice that there's a highlighted bit in the actual question. John tosses the coin 3 times. What is the probability that he tosses at least 1 head? And I think that's the question telling me to use this trick here. You could do it the other way, but it would take you a lot longer. So we're asked about the probability of at least 1 head, and I'm going to use the trick. It's 1 minus the probability of no heads. And so that's 1 minus the probability of tail, and tail, and tail. Now, I can just do my and or thing here. Actually, there are no ors, so it's just ands, and I get 1 minus 0.3 times 0.3 times 0.3. And if I do that, I get 1 minus 0.027, which is 0.973. Okay, so it's very likely I will get at least 1 head, which you would expect because, of course, it's biased towards heads. But there we go, I've used the trick at the bottom of the blue box there. Now, I know that these probability questions do get harder, and there is another tutorial with some much harder questions in it. So you might want to have a look at that too.
Okay, so we've had that first tutorial on conditional probability. Why was that tutorial conditional probability? Because you saw that the dark chocolate and the milk chocolate that were chosen at random, they were not replaced. So they say we should find probability that they were different. Probability that they were different means probability where you have dark and milk or milk and dark. Dark and milk, that's multiplication, that's independent probability, or means mutually exclusive event, or that's the branch, the other branch, milk and dark. So we do that, we get that probability. Is that okay? So this type of probability, the conditional probability. Okay. So conditional probability, they give room for us to, like, first one given, what's probability of the second one, or first one taken out, what's probability of getting the second one. So this I have explained from the beginning, and usually we write the conditional probability like this: P into A slash B. Probability of A given that B was already, so probability of A given B. Probability of A given B. This is how we write it. Probability of A given B. So this is used to connote conditional probability. So if we are writing conditional probability, you simply, to make it easy for you, probability of A, you write A bracket P bracket A given B. Given B, you write slash B. When they say given B, means slash B. Okay, so this is how we write conditional probability. So it's, in other words, to make it simpler, it means a scenario or a situation where you pick something from a box, something of different color, different whatever you want to use to connote this, without replacing them. So when you're not replacing, surely you will deal with a conditional probability. Let's take a look at this example. A box contains 3 blue. Okay, I think I give you this highlight. 3 blue counter and 8 red counter. A counter is taken at random and it's color noted. A counter is taken at random and it's color noted. The counter is then set aside and not put back into the box. So it's set aside, it's not put back into the box, meaning it's never brought back. A second counter is there taken at random. What is the and its color is also noted. So you take a second one from the box and the color is noted. Write down the probability that the second counter is red, given that the first counter was red. Probability that the second one is red, given that the first one was red. Now, first of all, we have 8 red, okay, 8 red counter and 3 blue counter. So probability that the second counter, so I'll use 2 for second slash 1, given that the first one was red. Okay, first red, you can say first red, 2 first red, and probably the second one red, given that the first one was red, this one. So to represent this conditional case. So if the first one was red, the probability of the first one being red will be 8 over 11. Probability of the first one being red will be 8 over 11. Now the probability of the second one, because you picked that out. So the total counters remaining is now 10. It's no more 11. If you pick it the second counter. But remember, when you pick the first one, you pick red actually. So total red remaining is no more 8 also. So the probability of the second one being red will be 7 over 10. 7 over 10. Because you remember the first counter you picked was, there were total 8 counters. The first one you picked was 8 over 11. Probability of the first counter you picked that was red. Probability of the red counter picked is 8 over 11. But the second time you pick it from the box, the counter you picked this time around was also red. Now they are asking us to calculate the probability of the second one being red, given that the first one was also red. So second one being red, after you pick the first one, there is no more 8 red counter in the box. So there are only 7 counter remaining for red. So, and there are a total of 10 remaining now, no more 11. So the second one being red will be 7 over 10. Second one being red will be 7 over 10, which is actually 0.7. Like I said, probably either we put in proper fraction or we put in decimal. Either we put the answer in proper fraction or we put the answer in decimal. Okay, so this is what this one is. Provided that the second one is red, given that the first one was red, that's what makes it a condition. That's why we call it a conditional probability. Like I said, conditional probability are usually used for things without replacement. Things that you pick from something randomly, from a box, from whatever, from a box usually, from anything. You pick things out randomly of different colors without replacing them. If you are replacing them, then it's a normal probability, normal combined event. It's not a conditional probability. It's not a conditional. It's normal combined event like the one we did in our previous video, now part 3 of this probability. Where we use the tree diagram to solve problems like you toss 3 coins once or 1 coin 3 times. These ones are not without replacement or with replacement. So when we're talking about without replacement, we're solely talking about conditional probability. Now let's take a look at the second question. Let's take a look at the second question. Now the second question says, the second, is it write down the probability that the second counter is blue. The second counter is blue, given that the first counter was red. Okay, the second counter is blue, given that the first one was red. We already know the probability of the first one being red. We know the probability of the first one being red is 8/11. Now, the B part of the question, we're solving problem 2. Okay, problem 1 was when we did this one. This one was question 1. Okay. Now, the B part of the question is a find probability that the second counter is red, given that the first one was what? The second one is blue. It's a find probability the second counter is blue, given that the first counter was red, given that the first one was red. Now, we already know the probability of the first one being red is 8/11. Now, the second one is blue, meaning blue has not been touched. Even in the first case, when you picked, you only picked red, you didn't pick blue. So probability of the second one is blue, second is blue, given that the first one was red, given that the first one was red, given that the first one was red, is, now in the second case that you're doing, you know the first time it was red, 8/11. The second one you pick it, the number of blue is still 3. No blue counter has been taken out. No blue counter has been taken out. So it's still 3. So we say 3 over, but not 3/11 this time around, because in the first case you picked one red out. So it's remaining a total of 10. So the probability will be 3/10. This probability will be of picking a second counter being blue is 3/10. Is that okay? Now let's go to another question of conditional probability. Now, the third question of conditional probability, he said the probability that the second counter is red, given that the first counter was blue. Okay, second is red, given that the first was blue. Now, let's find probability of the first one being blue. Probability of the first one blue, probability of first counter blue is what? First one blue is 3/11, right? If the first counter you chose was blue, this probability will be 3/11, right? First blue is 3/11. It's 3/11. Okay. Now, what will be the probability of the second one red, right? I think the second one was red. What's the probability of the second counter red, given that the first one was blue? Now, what it means, the total will always go down, because now we're picking the probability of a second counter red, given that the first one was blue. Probability of a second counter red, given that the first one was blue. So we already know the probability of the first counter be blue is 3/11. Now, what's the probability of second counter red? So, since the first time when you picked, you didn't pick red, you only picked blue. So the red is still remaining 8 in the second time that you're picking now. Because the first time you picked, the probability was what? Was 3/11. You didn't pick red, you picked only blue. So the probability of the second one being red is still 8, because it's still total 8 blue red counter remaining. But the total is no more 11, the total of the second one, we reduce to 10 because you've already picked one ball out, one counter out, which makes it remaining 10, the total remaining 10. So 8 over 4 is 8 over 10. If 2 go here, we get 4 over 5. We get 4 over 5, which is 0.8 if you want to change to decimal, 4 over 5, which is 0.8. So this is what this is, 0.8. Okay? So this is what we call conditional probability. This one is 0.3. This is what we call conditional probability. Given that the first one is this, what the probability of the second one being this. So you know, without replacement, you know replace. When you pick the first one, you did replace. So you know the total has reduced. You know the total has reduced. Now let's go to the D part of the question. Let's go to the D part of this question. Let's go to the D part of this question. Now the D part of the question says, the second counter is blue, given that the first counter was blue. The second counter is blue, given that the first one was blue. So probability, here we're looking for probability of the second one blue. We're looking for probability of second counter blue. Given that the first one was also blue. First one was blue. Given that the first one is blue. Given that the first one is blue. Okay? So now we already know probability of first one blue is 3 over 11. Probability of first one blue is 3 over 11. Now second one be blue means blue will reduce. Blue will reduce, will now be 2 over 10. Why is it 2 over 10? Because the first one you chose was blue. So blue, you remove one blue counter. It's now remaining 2 blue counter in the box. It's now remaining 2 blue counter in the box. So probability of choosing the second one be blue again will be 2 over 10. Because why is it 10? Because you remove the first counter, so the total counter remaining is now 10, not 11. So 2 over 10 is same as 1 over 5. It's same as 1 over 5. Okay? Which is 0.2. 1 over 5. Which is equal to 0.2 if you change to decimal. Okay, so this is a conditional probability. So any question that is telling you, oh, this taking without replacement, any without replacement, and something is picked at random from a box or from wherever, a place, a closure, something is picked out of them and the thing contains different color, different things, and without replacement, this type of probability is what we call conditional probability. It's what we simply call conditional probability. Now let's listen to another tutorial, maybe for a more tougher case, to be able to answer questions with regards to conditional probability. Okay?
Okay, in this tutorial we're going to look at some harder combined probability questions. Now hopefully you've watched the combined probabilities tutorial, because this key points box here is exactly the same. So I'm not going to go through that again. We're just going to get straight on with the questions. Now this question is harder because there are an awful lot of words and it might not be entirely clear what it's asking in part B. So let's read it very carefully. So each day John drinks 2 cups of coffee, and then we're given the probability that he spills the first cup is 0.3. And then there's a lot of information. If he does spill the first cup, the probability that he does not spill the second cup is 0.8. And if he doesn't spill the first cup, the probability that he doesn't spill the second cup is 0.6. And we've got to get all that information on a tree diagram. So let's try and work that through. Right, the probability that he spills the first cup is 0.3, so that's easy enough to put on the tree diagram. There it is. And now we need to use the fact that the total probability is 1 for each set of branches to fill in the other half of that set of branches, so that's 0.7. 0.3 plus 0.7 is 1, in fact. Right, now we have to go through this whole sort of thing with negatives and not negatives and all sorts of things. If he does spill the first cup, so we're in this place here, the probability that he does not spill the second cup is 0.8. So not spill is 0.8, which allows us to fill in the spill probability here, which is 0.2, again adding up to 1. And then if he does not spill the first cup, so that's this situation here, the probability that he does not spill the second cup is 0.6. So there's the 0.6 there, and that means that that one there is 0.4. And we have successfully negotiated all that writing and put it on a tree diagram. Then it says one day John spills just one of his cups. So that's either spill and not spill, or not spill and spill. And we're asked, is it more likely that he spills the first cup or the second cup? Well, I guess what we have to do for that is to work out the two probabilities and see which is bigger. So, the probability of spill and not spill, okay, is, well, I've written it out as instructed with ands, and now I'm going to use and equals times. Okay, so spill and not spill, taking that first highlighted set of branches, is 0.3 times, because it's and, 0.8, and that is 0.24. And then we do the other way around, so he doesn't spill the first cup, and he spills the second cup, and that's 0.7 times 0.4, which is 0.28. So on the day he spills just one of his cups of coffee, it is slightly more likely that he spills the second cup. Right, so there we go, and that is our answer. Okay, we're going to move on to the nightmare question now, and that is the one which is a combined probability question, but has algebra in it. And you may remember from the first tutorial we had a box of chocolates with dark and milk chocolates in it, and here's another one. This time it's got 10 dark chocolates and M milk chocolates. And quite a lot of people will be running for the hills now, but don't, because actually if you follow the rules, this isn't too difficult. So, what are the rules? Well, 2 chocolates are taken at random, so we need to decide on replacement. They're taken at the same time, so we treat it as if we have one followed by the other, and not replaced. So we need to remember that the numbers, particularly the number on the bottom, goes down by 1. And then we're told that the probability that they are both dark is 3/8. So that's the probability of dark and dark. Right, okay, so let's write down the probability of dark and dark. Now we've got an and, so we're going to use times. We need to know how many chocolates there are in total. So there are 10 plus m, or m plus 10 if you like, chocolates in total. Okay, so that's going to be important. And we can say the probability that the first one is dark is 10 out of 10 plus m. I'm actually going to write it as m plus 10 for a reason you'll see in a minute. Times another dark. Well, how many darks are left? Well, we've taken one out, so 10 has gone down to 9. This is the not replaced bit. And how many chocolates are there in total? Well, I had m plus 10, and if I've taken one chocolate out, that is, of course, m plus 9 left. Okay, so be very careful. The numbers have gone down by 1 on the top and the bottom. Okay, and we're told that that equals 3/8. So, we've followed the rules and we've written down an equation in m. And all we have to do now is sort that equation out and make it look like this. Well, the rules for solving equations are we get rid of fractions. So we're going to multiply everything here by the 8. And we're also going to multiply by the m plus 10 and the m plus 9. Okay, and that is going to be done to both sides. I'm going to leave it over there because I haven't got room to write it anywhere else. Now if I multiply all of this by that, the m plus 10 and the m plus 9 are going to cancel, and I'm going to get left with just, if I do that in red, I'm going to get left with 10 times 9 times 8. And if I look at the other side, and if I multiply the 3/8 by this, well, the 8's are going to cancel, and I'm going to get 3 times m plus 10 times m plus 9. Okay, now it's always a good idea when you're doing things like this to see if we can cancel, and I'm going to get the green cancelling pen out, and I can see that I've got a 9 on this side and a 3 on this side, and so 9 and 3 cancel to give me 3 and 1. Right, let's try and sort this out. So on the right hand side I'm going to use FOIL to multiply out these brackets, and on the left hand side, well, I just get 10 times 3 times 8, 10 3s are 30, 38s are 240, and on the right hand side I've got m squared, that's the first pair, m times m, the outer pair is m times 9, so 9m, the inner pair is 10 times m, so that's 10m, and the last pair is 10 times 9, which is 90. Okay, and then I want to get rid of the 240 on the other side to get a 0. So if we subtract 240 from both sides and simplify, we get 0 equals m squared. 9m plus 10m is 19m, and 90 minus 240 is minus 150, and we have done it. Okay, so nothing to be afraid of, we've just followed the rules and done a little bit of algebra, and we've done it. Right, having done that, we're now asked to find the probability that both chocolates are milk chocolates. So we need to find m. So we need to first of all solve the equation m squared plus 19m minus 150 equals 0. And that's just a question of factorising. Now, how you factorise quadratics is the subject of another tutorial, or even 2 other tutorials, but the basics are we're looking for two numbers which multiply together to give 150 with different signs. The bigger number is going to be positive, and the two numbers add up to 19. So without further ado, I'm going to tell you that those are 25 and minus 6. You could use the quadratic formula if you wanted to. And that gives me m equals minus 25, or m equals 6. Why? Because one of these brackets must be 0, so m is minus 25 makes that bracket 0, and m is 6 makes that bracket 0. Now obviously we can't have minus 25 milk chocolates, so let's cross that one out, and we know that we have 6 milk chocolates. And then we're asked to find the probability that both are milk. So the probability of m and m, again using the golden rule of writing down the probability we want with ands and ors if necessary, and then using and equals times. Remembering that we're not replacing the chocolates, so we need to adjust the numbers as we go, and so we get, well, there are 6 milk chocolates, which means there are 16 in total, and, so times, and once we've taken one milk chocolate, there are only 5 left, and there are only 15 in total. And if you do that and cancel down, you get 1/8. And so that nightmare question with the algebra is done. Just one more thing. Even if we didn't manage to do part A, because for whatever reason we had a mental block, we could still solve the quadratic equation, find m, and get part B right. So don't give up just because part A is hard. I hope all of that has helped.
Okay, hello, that's for the conditional probability. Now let's take some questions from our books. Okay, we've already got the hang of what we need to know regarding the conditional probability, right? So let's take some questions from the book. Okay, probably if we do have time. we might come back to take some of these questions. Is that okay? Now let's take a look at question number 3. The tutorial was very helpful, and we can see the difficult questions, the type of difficult questions you can find in the exam, right? You can lead you to a quadratic equation. You have to solve for m, and you use the value, the positive number, because they gave you 10 dark chocolate, and they did give you the number of milk chocolate, and the milk chocolate they represented with m, and we were able to find the probability of this. Okay, so now let's take a look at if we have this kind of scenario. Say the table shows a number of boys and girls studying math, art in a school. Math and art in a school. So this table shows the number of boys and girls that are studying mathematics, art in the school. Okay, so let's see what this will give us. Let's see what this will give us. Okay, so we have boys, we have girls, we have total, we have girls, then we have total, meaning we still have to run one more. Yeah, we have total number of students, so we write total. Okay, so we have maths, we have mathematics, we have art, students taking art subjects, then we have total number. Okay, so here we have for boys we have 26 students. And therefore taking mathematics, and we have 14 taking art. We have 14 students taking art. So the total of that is 26 plus 14, which gives us 40. Okay. Then for girls, we have 34 students taking mathematics. We have 34 students taking mathematics, and we have 12 students doing art. So that gives us a total of 46. That gives us a total of 46 students. Now, if you decide to sum up the total number of students doing mathematics, whether boys and girls in the class, you get 60 here. And if you decide to sum up the number of students doing art, whether boys and girls, you get 26 here. So if you add the total here plus the total here, you get 86. 40 plus 46, you get 86. So this is the table we have. So this is the table we want to use to ask some probability questions. It says a student is chosen at random. Calculate the probability that they study mathematics. Okay. A student is chosen at random. They're not telling you whether it's boy or girl. Probability A part of the question. Probability a student is chosen at random. Find probability that they study mathematics. So P maths. So what we do, we find the total number of students that are doing mathematics, whether they're boys and girls. The total number of students in the class that are taking mathematics. So let's find the total number of students taking mathematics. For boys and girls, 60. So you can see the total people taking mathematics is 60. Okay, 60. So the total number of students taking mathematics is 60. Out of a class of what? Out of a class of 86. The total students in the class is 86. So probability of students doing mathematics will be what? Probability of maths will now be what? The 60 students that are doing mathematics over the total students in the class. The 60 students that are doing mathematics over the total number of students in the class. That gives us 60 over 86. So we can simplify this. 2 can go into 30, 60, you get 30. And 2 can go into 86, and you get 43. 2 go here, you get 43. 43 is a prime number, right? So since it's a prime number, we cannot reduce further. So that gives us that solution. When they say that you should find the probability, calculate the probability that they study mathematics, that the students choose at random, that you should find the probability that the students study mathematics. So we have to find the total number of students that are doing mathematics in the class, which is 60, whether they are boys and girls. But if they say find the probability that the students who study mathematics are boys, you now say 26 over the total, 26 over 86. But they did say boys or girls. They just say find the number of students study mathematics. So total number of students who study mathematics is 60. So 60 over the total number of students in the class, which gives us this probability. Is that okay? Now the big question might be more specific. Let's take a look at the big question. The big question. Okay, the big question says a student is chosen at random. Calculate the probability that they study maths, given that the student is a girl. Now, this is where it makes it conditional now. The big part of the question is what makes it conditional. It's a given that the student is a girl. They give you a condition, meaning they're not interested in the total number of students doing mathematics. Look at the question. Say a student is chosen at random. At random, they just choose a student. They did look whether a boy or girl. They just chose at random. Calculate the probability that they study mathematics, given that the student is a girl. Now they give you a condition. They give you a condition, given that the student is a girl. So probability that the student study mathematics, given that it's a girl, we're going to look at the number of students, number of girls who do mathematics, and the total number of girls in the class. Okay, so the student study mathematics, given that the student is a girl. So this one makes it conditional. Okay, without replacement and a conditional statement, given that this person, given that. Okay, they ask you to find probability of this, given that this. Okay, so find probability that the student study mathematics, given that the student is a girl. So here you cannot look at the total number of students who study mathematics, but you have to look at the total number of girls that are doing mathematics. So the total number of girls that are doing mathematics in this class, girls doing mathematics, because this is the color for mathematics, girl doing mathematics is 34. And we cannot say over 86 because we're looking at the total number of girls, over the total number of girls. Okay, so this probability will be the number of girls that are doing mathematics over the total number of students in the class. Number of girls that are doing mathematics over total number of girls in the class. So we say this will be 34 over 46, because the total number of girls in the class is 46. 34 over 46. Okay, I think we can reduce this by saying 2 can go here, 34, you get 17. 2 go here, divide this by 2, you get 17. And divide the denominator by 2, you get 23. Supposedly, you get 23. So this will be our probability, 17 over 23. Okay? So you can see a conditional. This is how we apply conditionality to our probability. So find the probability that the student studying mathematics is a girl. The number of students studying mathematics given that it's a girl. So in this case, we are dealing with the girl as a condition. Now, see, let's take a look at the C question that comes. Let's take a look at the C questions there as it were. Now, the C question says, okay, sorry, that's all for this question. Let's take another question, question number 4. Let's take another question number 4. Question number 4, okay? Now, for question number 4, we want to apply, you remember in part 2, of our work, we applied the Venn diagram. We did the Venn diagram, part 2 of the probability concept. We applied the Venn diagram. So we want to use the Venn diagram to study conditional probability. We want to apply conditional probability to Venn diagram. We're also going to apply it to a tree diagram. After that, we call this class a day. So we have two more concepts to apply conditional probability before we'll be rest assured that you're good to go. Once we do that, we'll be rest assured that you're good to go with probability. We're done with probability. Then we'll move to statistics. Okay. Now let's take a look at applying it to a Venn diagram. You see, the numbers 1 to 50 are arranged into two sets of numbers, where O is odd numbers and P is prime numbers. Now O is odd numbers, so O is odd. So I'll just say O equal to odd and P equal to prime numbers. O is odd numbers and P equal to prime numbers. Prime numbers. We know prime numbers. Numbers that can only be divided by itself and 1. They are called prime numbers. Okay, we know odd numbers. Numbers like 1, 3, 5, 7, and 9. These are odd numbers. Even numbers are 2, 4, 6, 8, like that. Okay, so they're giving us number from 1 to 15, and they're telling us that probably 1 to 15 might be just be the universal set. They're giving us numbers. You see, the numbers 1 to 50 are arranged in two sets of numbers, where O's are the odd numbers and the P's are the prime numbers. Represent this information in a Venn diagram. Okay, so let's represent the first part of the question is for us to represent the information in a Venn diagram. Okay, this information, number 1 to 50. This is the universal set. Remember the symbol for universal set. So the universal set is 1 to 50, and here we're going to write the odd numbers. So I'm going to draw two circles. We're going to draw two circles, one for odd numbers and the other one for prime numbers. One for odd numbers and the other one for... Definitely they will overlap. Why? Why are we sure they will overlap? Because there are prime numbers that will be odd numbers. It's that many prime numbers are odd numbers. Therefore they overlap. Okay? They overlap. Now let's list the prime number from 1 to 50. Let's list them here. Only the prime numbers that are odd numbers. 2 is a prime number, but it's not an odd number. So 2 cannot be here. 2 cannot be in the overlap. Is that okay? 2 cannot be in the overlap. 2 can only be here because it's a prime number. 2 can only be here. So let's say this is the odd number and this is the prime number. And then let's draw the universal set to enclose it. Okay? Now let's list the numbers. Let's list the numbers that are overlap, that are between the prime numbers you can list them out. You can write the odd numbers. What are they? What are the odd numbers? Of course, odd numbers are 1, 3, 5, 7. Okay, when we get to 50, we stop. 7, 9, 11, 13, and 15. Right? These are odd numbers. These are all the odd numbers. What are the prime numbers? Prime number starts from 2. 2 is the only even number that's a prime number. The rest are odd numbers. So 2 is a prime number. So we have 2 here. 3 is a prime number that can only be divided by itself and 1. 5 is a prime number. 7 is a prime number. But 9 is not a prime number because 9 can be divided by 3. So 9 is not a prime number. But 11 is a prime number. 30 is a prime number. 50 is not. Why? Because 50 can be divided by 3 and it also can be divided by 5. So prime numbers that are prime numbers are only numbers that can be divided by itself and 1. So if you have this, you can find the intercept, P intercept. To find the numbers that are here, in case you don't know, you can simply say What are the P intercept O? Prime number intercept odd numbers. What are the similarity? What they have in common? You can list them out. And those ones are the ones we're going to list in this middle. So what are the numbers that are here and here? 3 is in both. So 3 is common, it's overlap. 5 is in both. 7 is in both, right? 7 is in both. 11 is in both and 13 is in both. So you have 11 and you have 13. So these are the intercept. Intercept means the number in the overlap. These are the intercepts. So all of this we're going to list them. We're going to list them here, this place, this overlap. So I'm going to write 3, 5, 7, right? 11 and 13. These are the numbers that fall in the overlap. That is a intercept, that is intersecting between this. So if that is true, now look at P. Which numbers are remaining? It's finished. The only 2 we put here. 2 is the only one that was not used in the overlap. So you put the 2 here. Now look at the O. 1 we've not used 1, right? 1 is part of the number. So I put 1 here. Which other number we didn't use? Which other number we didn't? 9. We didn't use 9 and 15 because 9 was not there as in the overlap. 9 and 15. So we put 9 here and we put 15 here. Then all the other numbers from 1 to 15, they will be outside. Like for all the even numbers, like most of the even numbers, apart from 2. Okay, apart from 2. So 4, starting from 4. 4 will be outside because it's not in O, it's not in P. Because we say number 1 to 15. So we've not used 4, we've not used 6, we've not used 8, we've not used 10, we've not used 12, we've not used 14. So all those ones, you're going to write them outside, anywhere outside the 2 overlap. So you have 8, you have 10, you have 10, you have 12. You can write them anywhere as long as it's outside these two circles. You have 14, okay? So these are the other numbers, they are out here. So you've done what they've asked you to do, the first one. Don't worry, this is not the prime. The prime is the probability. We're coming to the probability. Here is just a show of honor, what they want you to do, to refresh your set notation, okay? To refresh your knowledge on set. Then the B part of the question says, a number is chosen at random. Calculate the probability that it's a prime number. A number is chosen at random. This is not a conditional yet. This is a normal probability. So, a number is chosen at random. A number is chosen at random. Calculate the probability that it's a prime number. So, how many numbers do we have in the prime? How many numbers do we have for prime? And remember, the total number is 15. 1 to 50 is 15. So, how many do we have for prime number? 1, 2, 3, 4, 5, 6. There are 6 numbers for prime numbers. So, the probability that the number chosen at random is a prime number, you say number of prime numbers over the total numbers in the whole universal set. Number of prime numbers, so you can say number of prime number of prime number over total. Okay, so we just say over total. Okay, so which means 6 over 15, which means 6 over 15, which means the probability is 6 over 15. So here we can simplify, right? 3 can divide 6 and 3 can divide 15. So when 6 divided by 3, you get 2. And 50 divided by 3, you get 5. So our answer will be 2 over 5. Probability answer is 2 over 5 or 0.4. I think if you change this one to decimal, you're going to get 0.4. Okay? You're going to get 0.4. So that's it. So you can see the first case we are asking you to do set. Second case we ask you a probability question. And probably the third case we're going to ask you a conditional probability question. See how the question progresses from just representing the information in the Venn diagram. The next thing, ask you a normal probability question. The third one, we're going to ask you a conditional probability question. So you can see the progression of the question from known to unknown. Now, the third one, which is the probability, which will involve the conditional probability, where the application, the reason for this chapter, is that a number is chosen at random. Calculate the probability that it's a prime. Calculate the probability that it is a prime, given that it is odd. You see, they give you probability that it's a prime, given that it is odd. Probability that it's a prime number. So I'm going to probability. They say we should calculate the probability that it's a prime number, given that it is odd. There's a condition. Probability that it's a prime number. So prime number, given that it is odd. Probability that it's a prime number, given that it is odd. Because remember, not all the prime numbers are odd numbers. There's 2. 2 is a prime number, it's not an odd number. So now they're asking you to look at the condition of odd numbers. So if you count the odd numbers, odd numbers, how many odd numbers are in the prime number? Starting from here. So if we count the odd numbers, if we count the odd prime numbers, how many? 1, 2, 3, 4, 5. There are 5 of them because you not count this one. It's not odd. 2 is not odd. So we have 5 over what? 5 over what? Okay, 5 over what? Is it given that it's odd? So we already know that the odd is the number odd. So we already know the number odd. Therefore, the total number of possible outcome is only 8. Okay, we already know the odd numbers. Count all the numbers, odd numbers from 1 to 50. Because they say given that it is odd. So our total will not be over the 15. Because if you say over 50, you are adding the even numbers. Like 2, 4. We're going to take them out, all the even numbers. 1, 2, 3, 4, 5, 6, 7. So 15 minus 7 will be 8. If you take all the even number out from the total numbers, you say all the even numbers are 7. So 15 minus 7, I will get 8. So the total odd numbers that are from 1 to 50, they are 8. Total odd numbers are 8. Okay? So you say 5 over 8. The total odd numbers. Because you must do it over the total of this odd. You must not say over the total of all the numbers. Okay, that's why it's a conditional probability. We must do it over the total of this odd number. Given that, that's why they gave you this condition. This is why the condition is paramount. This is why this condition is very paramount. So you must do it over the total of whatever is here. Over the total of whatever is here. So the total cannot be the total of all the numbers in the set. Is that okay? So that's it. It's as easy as that. It's as easy as that. That's the conditional part of the question. Now, the last but not the least for this application is using it for a tree diagram. We are taking examples from every aspect of probability that we studied. So to make it very conducive and make it more elaborate for application for IGCSE and even possibly A-level, the AS of the A-level. Now let's take a look at another question, probably maybe without replacement. We want to apply it to without a replacement question. How do we use it to solve the tree diagram? How do we use the conditional probability in the tree diagram? Now let's take a look at the question. A bag contains 10 red. I will only be writing the numbers. Okay. A bag contains 10 red. So 10 arrow. A bag contains 10 red, whatever it is, whether ball or whatever, 10 red beads. In this case, beads. A bag contains 10 red beads and 5 black beads. How many black? 5 black beads. 5 black beads. Okay. Now, a bead is taken out of the bag at random and its color is noted, and then it is not placed back in the bag. So, meaning without replacement. So, we're talking about without replacement, which means every time the total number goes down by 1, right? Without replacement. A bead is taken out from the bag without replacement. Without replacement. The color is never put back into the bag. So the first thing is draw the tree diagram to show the possible outcomes and the probability of the first 2 beads removed from the bag. So the first thing they ask us to do is to draw the tree diagram. Okay? To draw the tree diagram. Okay. Now, of the possible outcomes, of all the possible outcomes. So we're going to have, let's say we have, let's use the black to draw the tree diagram. So we have the first one be red and the second one be blue bead. So, and then here we have, for these branches, we have also, for the second case, for the second choice we make it, first one red, second one bead, and also here, first one red, second one blue. Okay, now let's fix the red first. Probability of the first one be red, okay, is here, arrow, and the second one be blue. Okay, let's fix the red. Okay. Now let's fix the blue. So this branch, remember every branch total probability must be 1. Probability of first one be red, and this probability of the first one be blue. Probability of second one, this first will I say first choice, second choice. So here you can say first pick, and this second pick. Okay, you know we're picking the bead out of the bag or whatever. Okay, now this is a blue. Now we're going to fix all the probability. Remember they say they are 10 red. So probability of the first one be red will be 10 over 15. There's total of 15. There's total of 15. So probability of the first one be red will be 10 over 15. Right? Now let's write that probability. Probability of the first one be red is 10 over 15. What will be the probability? It's not replaced. After it's taken, it's not replaced. What will the probability of the second one be red? Red will go down by 1 because if the first one was red, pick it again, the second one will be 9 now. 9 red because you remove 1 red. Over the total will also go down by 1. The total will be 14, 9 over 14. So that's what you get here. Okay? That's what you get here, 9 over 14. You have to fill up this thing. They're not going to tell you. If here is 9 over 14, what will here be? Probability that the second, if the first one is red, what is the probability that the second one is blue? Blue is 5. Blue has not been touched. Blue is 5. Blue has not been touched. So here will be 5 over 14. But the total has reduced because you picked the first one. Here will be 5 over 14. Okay? So you must learn to fill up the table. This is very important, the probability table. Then, now if what's the probability of the first one being, probability of the first one you pick is blue. There are 5 blue and there are 15. So this will be 5 over 15. Probability of the first one you pick is blue is 5 over 15. Now, what's the probability of the second one is red, given that the first one was blue. Second one is red. So the total red has not gone down because when you pick the first one, red was not picked. But the total has gone down to 14. The total would have, because you're picking the second one, total will go down to 14, not 15. Now, let's see this way. What's the probability of the second one being blue, black? Sorry, not blue, black. Okay, what's the probability of the second one being black? Given that the first one was also black. So this one will reduce to 4. And the total will also reduce to 14. Right? Reduce to 4. Because the first one you picked was black. You got 5 over 15. Second one, black has reduced now to 4. And the total also reduced to 14. So this is the probability tree. And this is what the question, this is what they asked us to do. We should draw the tree diagram to show the possible outcomes and the probabilities of the first 2 bits removed from the back. We showed all the probability of the first 2 bits, all the probability of the first 2 bits removed from the back. If they ask you what's the probability of picking different colors, there are two different colors. There are 2 different colors. Okay? These are 2 different colors. Now, if they ask you probability of different color, this is red and black. It's a different color. Or red and black. So they ask you what's the probability of picking different color. You say 10 over 50 times 5 over 14. Then plus you do this second branch, another different color, black and red. So there are 2 branches for different color. What probability of picking same color is red and black. Okay, and blue or black, whatever the color is. Okay, what's the probability of picking same color? What's the probability of picking same color? Red, this way, red, and blue or black, whatever we call it. Okay, this is the probability of picking same. So this times this, then plus this times this. If you ask the probability of picking same color, in case the question comes in the exam. Okay, so we should be able to understand this concept in details, not just trying to just go through it and forget about it. Please try and get a hang of it. Now let's go to the second question that they can ask from here. Okay, the second question that could be asked is calculate the probability that the first 2 bits are red. Probability that the first 2 bits, this is so easy, meaning only this branch. The first 2 bits are red. They didn't ask of same color. They just say probability of the first 2 bits are red. What's the probability of the first 2 bits are red? Now, probability of the first 2 bits are red is probability of the first one red, probability of the first one red, and probability of the second one red. So red. So we have them in the table. We have in the tree. The first one red is 10 over 15 multiplied by, this independent event. So 10 over 15 times, because when you pick it, the second one is not dependent on the first one. It's independent event. So that's why we use times, we multiply. We say and the second one being red, which is 9 over 14. So 10 over 15 multiplied by 9 over 14. Okay? That's the probability for this concept. So after that, we multiply this and simplify. We can easily simplify without making hollow value of it by saying 3 go here. 3 go here, I get 3. I want to break it down. If you don't want to use calculator, 3 go here, we get 5. Right? Now another thing we can do, 5 divided by 5, we get 1. 10 divided by 5, I get 2. Right? These 2 can go here. 2 divided by 2, you get 1. 14 divided by 2, you get 7. So everything left is only 3 over 7. So without pressing calculator. Another thing is to multiply the numerator and multiply the denominator. But simply, you can just cancel out. You get 3 over 7. So you see, it helps you to simplify to the lowest term when you do cancelling out. So we get the probability of both first one red, second one red being 3 over 7. Okay, so that's that for that. Let's go to the third one, which probably will include conditional probability. The third one, the third case, this is the B question. Okay, let's go to the C question, which we normally include, this is A question. Drawing the tree diagram was the A question. Okay, and then let's go to the C question. The C question will probably include a conditional probability, will be a conditional probability. In fact, it's the reason why we are applying it to this type of question. Is that okay? Without a replacement. We use the tree diagram to solve without a replacement question. So what is left for us to find more questions to solve? Okay, you pause the video, you watch it severally, and then you look for this type of exercise question. Solve them from textbook and solve them from past paper. This is how to master it. Okay, now let's take a look at the C question. C question says, calculate the probability that the second bead is black. The second bead is black, given that the first bead chosen is red. So probability that the second bead is black, given that the first one is red. So this is what makes it a conditional probability. probability that the second one, probability that the second bit second is black, given that the first one was red. Given that the first one was red. Right? Let me see again. It says calculate the probability that the second bit is black, given that the first bit chosen is red. Okay, where do we have second black and first one red? We have here first one red, this branch, right? This branch. First one red, and then the second one is black. This is where we have it. This branch. Is there any other branch where we have such? Is there any other branch where we have such? Probably that the second bit is black, given that the first one was red. The first one was red. Okay, let's do that first. So we have, we said this branch, right, which is a PRB, right? PRB. And we must do the total of red. Second one be red. Okay, sorry. Okay, so we have P, second one is black, do that the first one is red. So we have the probability 10 over 15. The first one was, given that the first one was red, 10 over 15. 10 over 15 times the second one be black. The second one be black is let's see the question again. It says calculate the probability that the second bit is black. The second one is black. Okay. Calculate the probability that the second bit is black, given that the first bit chosen is red. So we say, as the first bit is already known to be red, then the bottom half of the tree diagram can be ignored, right? We can ignore the bottom half of the tree diagram, right? We can ignore the bottom half of the tree diagram because the condition has already told us that the first the condition that the second bit is black, even that the first one is red. So this half bit, there's no red in the first case. So we only go to deal here. We only go to deal here. So that's the first thing we should note, right? So we should, with the first half of the tree diagram, will be ignored. So because it involves a black bit having been chosen first. Right? Because it involves a black bead, right? Are you with me? We say as the first bead is already known to be red, the first one is already known to be red, then the bottom half of the tree diagram can be ignored because it involves a black bead having been chosen first. So we're going to ignore this one. This one, why are we ignoring this? We are ignoring this because we are ignoring this whole thing because it's telling us that the first one is black. They are saying that the probability that the first one is red. So this whole branch, this whole thing, we're going to ignore it. We're going to ignore this whole thing. Why? Because it's giving us a situation that the first one chosen is black. This one is giving us a situation that the first one chosen is black. And the question says, given that the first one chosen is red. So given that the first one chosen is red. So find the probability that the second one is black, given that the first one chosen is red. So we're only looking at this branch. We're only looking at this branch. Let's change the color. We're only looking at this branch. Right? We're only looking at this particular branch. Because this is where we have the first one chosen to be red. This is the branch area where we have the first one chosen to be red. Right? Because they say find probability that the first one is black, given that the second one is black, given that the first one is red. So we cannot, this one does not have that first one chosen to be red. Does it have it? So we're going to ignore. So here we say ignore. Ignore this branch, the lower side of the branch of the tree. You ignore it. You ignore. Is that okay? You ignore. So you concentrate on the upper part of the branch. Right? We're going to concentrate. Now the top half of the tree diagram has a total probability of, what's the total probability of the top half? What's the total probability? Is it 2 over 3? Can we check? What's the top half of, what's the total probability? Right? The top half of the tree has a total probability. Now, that is, we look at 10, this one, 10 over 50 times 9 over 14, right? Plus 10 over 50 times 5 over 14. That's the total probability. Because we have to find the total probability before we do this branch over the total. Someone with me? First of all, let's find the total probability of the top half of the tree. Because what the question, we're actually using only this branch. But this branch over what? Over the total of the top half. So let's find the total of the top half before we say this one over the total. You get it? So please pay attention. We're going to ignore the lower black. I've already explained why we ignore this one. Because they say find probability of the second one be black, given that the first one is red. This one, the whole branch downward, this down branch does not have the first one be red. So the whole of this we ignore it. But let's find the total probability first. This is the biggest question you see in the exam. Like, it's easy, but this is the biggest level they will make you read up to for Cambridge. Okay, so you're going to find the probability that the second bead is black, given that the first one is red. It looks easy. I know what you're going to do in the exam is just say 10 over 50 times 5 over 40. You think the answer is just that. No. You're going to do this over the total. First, let's do the total. For the total, let's calculate the total probability for the top branch, for the whole top. For the whole top. For the whole top, we have 10 over 15. 10 over 15 times, for this branch first, this branch, red, times 9 over 14. 9 over 14. Then you can put bracket, okay, to show that you're dealing with this arm and this arm, red. Then you say, or this branch. We're going to another branch now, another way. This one, this green highlight, okay? Or in probability use plus, because or is for mutually exclusive event, which means probability of this one occurring, we prevent this one from occurring. Okay, so we now say or 10 over 15, which is this branch, this one, 10 over 15. We're doing the total probability for the top over 10 over 15 times 5 over 14 times 5 over 14. We multiply by 5 over 14. So when we do that, we get the total probability for the top accolade. We're going to get the total probability for this whole, this one I highlighted with the red. Let's find the total probability. So if you do cancellation, like you do what cancel here and there, we eventually get something very significant. Like for example, you say 3 go here, you get 3 here, 3 go here, you get 5. I think we've done this calculation before. 5 go here, you get 1. 5 go here, you get 2. 2 go here, you get 1. 1 go here, 2 go here, you get 7. So from here we have 3 over 7 left. From this one, we have 3 over 7 left here. Plus, let's do cancellation for the other one and see what we have. Here, what can go? 5 goes into 5, you get 1. 5 goes into 50, you get 3. Right? Any other thing can cancel. 2 go here, you get 5. 2 go here, you get 7. You get 7. So if there's nothing can cancel, 5 times 1 you get 5. And 3 times 7 you get 21. So if you add this together, in your calculator, I think you're going to get overall of 2 over 3. You're going to get overall of 2 over 3. So you can do this. So the total probability for the top branch is 2 over 3. The total probability, the total, okay? Now, but that's not the question. The question is asking you to find the probability that the second one was blue, was black, given that the first one was red. Okay, you're going to do that over this total. Whatever we want to do on this branch now, because this is what they want, this is the branch they're interested in. Over the whole total. Are you with me? Over the whole total. So the probability of the first one, red, is 10 over 15. First one, red, is 10 over 15. 10 over 15 times the branch, this branch. You know, now we're solving this branch, the real question. 5 over 14 times 5 over 14 times 5 over 14 all over everything over 2 over 3. Everything over the total probability of the whole top branch. Everything over the total probability of the whole top branch. Do you understand? Everything, just like when we can, you know, the total has to only be dependent on this branch, because that's only where we have red for the first probability. So over this, so we can cancel this one out like we did. 5 here, we get 1. 5 goes here, we get 3. We get 3. We can change the color to make it more conspicuous. And then 2 here, we get 5. And 2 here, we get 7. So 7 times 1, we get 5. Right? We get 5 over 21 for the numerator. We get 5 over 21. Right? And the denominator, we have 2 over 3. So we can now solve this fraction. If you solve this fraction, we're supposedly going to get something interesting. So you get 5 over 21, if we're not mistaken, divide by the denominator, this 2 over 3, divide by 2 over 3. So in division, you change this one, 2 over 3, not 2 over 5, 2 over 3. You change this one to multiplication, and you flip this one. So it becomes 5 over 21, 5 over 21, times 3 over 2, times 3 over 2. Okay? 3 over 2. Now we say 3 can go here, 3 here, 1. 3 go into 21, we get 7. So the numerator, we get 5 times 1, we get 5. In the numerator, 5 times 1, we get 5. And the denominator, we have 7 times 2, we get 14. 7 times 2, we get 14. So our answer is 5 over 40 for this probability. This is the biggest question they will give you from a tree diagram. Please take note. Please take note. Okay? In the exam, they can say, what's the probability of getting the second one red, given that the first one was black? For example, you know, here we did this for this branch. In the exam, it could be, what's the probability of second one red, given that the first one was black? So in that case, we're going to ignore the top, because the first one must be black. So you ignore the top, and you find the total probability for this branch and this branch. You add them together. You do this times this plus this times this. You get the total probability. Then you do the probability of this only branch over the total. You get the answer. Okay? This is the biggest question you're going to get in Cambridge IGCSE. So with this, we come to the end of today's class. Thank you for joining us.